Okay. Hi everyone. Welcome back to our VAPS seminar. Today we have Jiwoong Jang, who is currently a Novichok postdoc fellow at University of Maryland. He's gonna talk about periodic homogenizations of geometric equations without perturbed correctors. Please, Jiwoong.
Thanks for the introduction, and thanks for the opportunity to give a talk. And thanks so much for coming to the talk. In this seminar, I'd like to introduce my work on homogenization of geometric equations. Okay. Our interest of the talk is in homogenization of geometric evolutions of the fronts in a periodic environment, and the environment is heterogeneous, and then it is assumed to have CN periodic set patterns. The pattern is modeled in the spatial variable, so we'll have a zero periodic environment, and so we will zoom out, and as we are zooming out, the heterogeneities become more micro, and it will be very highly oscillatory. So the fronts will go through the highly oscillatory environment as well. So the surface will be very highly oscillatory. So as we are looking far away, we will see some average behavior. So if there's a really average behavior, then we say homogenization happens. Sometimes the homogenization does not happen. It depends on cases, and then we will see examples. And there are two main motivations to this study. The first one is the first mean Kirchhoff law. The normal velocity is the mean Kirchhoff plus the forcing term. And when the hypersurface divides the space into two regions, and the two regions are occupied by different matters, and the first term comes from the difference, the discrepancy of the work energies of the matters. So C is the forcing term is the difference of the work energies, and then now the environment is heterogeneous in the spatial variable. So the phi plus minus are a function of x. The forcing term is also a function of x as well, and it is a ZM periodic. And the front or hypersurface will be seen as a zero level set of a certain function, and the function will be seen as a viscosity solution to this problem. And here, for instance, the big parenthesis is the normal velocity. And the other motivation is the curvature equation, and now there is a wind from the environment, and the wind is given by the problem. In the picture, we have two flame fronts at time 0 and at time 1. And the study by Marstein introduced the curvature effect for the flame front. For instance, the concave part burns faster and the convex part burns slower. Sometimes the front recedes back. But the cutoff correction was introduced by Zhu and Roney. Here we have the cutoff correction, and that is to prevent the unburnt phenomena. For instance, we have the already burnt region at time 0, but the flame front recedes back at time 1, but we still have the burnt region because it's already burnt. So the region is not unburnt, and the correction is to prevent that unphysical phenomenon of unburning phenomenon. Now we will see its homogenization. And to introduce the corrector problem, let us consider the formal answers. So we have the expected highly oscillatory surface. Now we also expect to average the behavior, which is described by U. So you have some certain, in a local variable, we have a certain flat surface of U of xt, and we separate the two scales, x and y, and the y is x over epsilon. So y will go through the oscillatory effect, and it's very fast variable and the local variable. And the x is a global variable, and it's also slow variable. And sometimes it is called a macro variable. And in the formal ansatz, so we separate the two scales, and the x is kind of freeze in the formal ansatz. The t is also a global variable and also freeze in the formal ansatz. So they are kind of fixed in the formal ansatz. So we have a fixed address of the problem, and so now we have the gradient of the u of xt denoted by p, and the p is fixed. So we have a certain normal direction, and associated with that direction, we have the corrector from the direction, and the corrector is denoted by v. And the v is a function of y, which is a fast variable. So we have the correct term v, and this is multiplied by epsilon. This is following the spatial scale, which is epsilon. So epsilon is multiplied to the character, and we add them. So in the formal answers, we believe the u epsilon is described by the sum of the average behavior by u plus epsilon times the correct term. So we put this formal ansatz into the equation and we perform the differentiation in y. And we already separated scales and we kind of think that epsilon is already set to zero, then we have this local problem. Now x over epsilon becomes y runs the torus on the cell. And the p, which is the gradient of u, is already fixed vector. And here we have the time derivative of u of epsilon, and this will also form the slow variable, which becomes just a number. And that is moved to the on the right hand side, which is denoted by f bar of p. Then we will see that that is basically the average speed or the effective speed. That comes from the average direction for the fixed direction denoted by p. And there is almost one real number that allows a viscous solution to this local problem. So the number is well defined for every p. So we have at least the quotient is defined. So we have the last line of the equation. So the limit function solves the last line equation, which is so-called the effective equation. So the local problem is called the cell problem, and this is from for every direction for every p. And if we have a character, the solution is character. If we have a character, then we have a traveling wave solution with the speed negative bar p, and with a spatial profile that is almost planar because the p times x corresponds to the planar part, and we have the correction term is sometimes v of the x over epsilon. And here v is bounded because it's solved on the compact domain. We have the almost planar profile. So it is uniformly flat. We have a uniform bound for the traveling wave solutions, and actually it is vice versa. If we know the uniform flatness behavior of the traveling wave solutions, then we can recover the viscosity solution V, which is corrector, by using the Parents method. We can find the solution. So if we happen to know that the every cell problem is solved for every directions, and if we know all the uniform flatness behavior for every associated directions, and then homogenization can be proved and by Evans. It is proved by Evans, and the framework is called the classical perturbed test function method. And Evans proved the convergence for first order Hamilton-Jacobi equations and the second order uniformly analytic second order equations. So it has been a classical belief that if we know the characters for every directions, and the homogenization will be proved by this classical method. It has been a classical belief, but the story is more complicated for geometric equations. There is a subtle issue, and I'll come back to this point later. And here's the literature of the first mean culture flow. Leon's Suganides gave a condition on the forcing term that guarantees the solvability of every cell problem for every direction. Here we call it condition star. The condition star can be seen as the small oscillation condition on the forcing term. So for instance, if we have this condition star, then the forcing term cannot be zero somewhere, otherwise it's not true. And must have a certain sign. First, the C is positive, since C has a certain magnitude, and by that magnitude of the forcing term, the gradient of the forcing term is controlled by the condition star. So the oscillation of the forcing term must be controlled, must be small. And then they use the Bernstein method to prove the equilipsis estimate, which is uniform in lambda and sigma. Here, lambda is the approximate parameter, and sigma is a regularization parameter. So they took the limit to recover the viscosity solution of the cell problem. So they found the characters for every directions. And there is another small oscillation condition on the forcing term proved by D. Crowley-Eve. Um, the paper proves the existence of effective speed and the uniform fluency behavior of pulsating waves under this small condition that the C to norm of the forcing term must be small. If it is small enough, but it can change its sign. If its C to norm is small enough, then we have the effective speed and the uniform fluency behavior. What if the oscillation of the forcing term is large? Then Quadradiag-Williams-Suganidis constructed an example of non-homogenization where we lose uniform flatness. So they consider the 2D setting with a laminated structure. Here, the laminated structure means that the environment where the forcing term is constant along some axis. So in the picture, we are taking the x2 axis as the reference axis along which the forcing term is constant. So now the forcing term is a function in the variable only x1. So we have the function g, and here there is a stationary set in the middle. We have the line at 1/2, and the line does not move, and the g is taken to be 0 on the line, and the curvature is 0, so it is a stationary set. So it separates the cell into two regions, two channels. In the second channel, the forcing term is very large negative numbers, very large negative function. So there is a super solution that goes down with a certain speed in the second channel. And in the first channel, the opposite happens. We take the very large positive function so that there is a subsolution that goes up with a certain speed. And it creates a long fingering phenomenon. In the sense that here, so if we start with this initial hyperplane, and as time goes by the barrier function argument, we have this at time one and at time two. As time goes by, it diverges, so we lose uniform flatness behavior. And also, there's no well-defined average speed. There's no well-defined effective speed. If we start with this initial hyperplane, then we can prove that U7 does not converge. So we lose homogenization. What if C is just non-negative? A similar idea is applied. So in the second channel, there is a G. G is taken arbitrarily. And then there's a certain behavior of the front in the second channel. Then there might be some solution that goes up with a certain speed. So C epsilon is kind of prescribed. According to that prescribed speed, we design a very large oscillating forcing term in the first channel, which is very large. This is taken to very large, so that it creates a certain subsolution with a speed at least C plus, which is at least larger than C minus, still larger than C minus, so that it creates a long fingering phenomenon. Then it creates a long fingering phenomenon, so we lose convergence. So this is also an example of non-homogenization. In 3D or higher, Caffarelli-Monneau show the non-homogenization even when C is just a positive forcing term. And their example is this. Their example is the rolled version of the previous example. Here now we have a cylinder. On the cylinder, the forcing term is taken to be just 1. So we have outward forcing term 1, and we have inward curvature effect by 1 because the radius is 1. So the two forces are balanced on the cylinder, so the cylinder is a stationary set. And the cylinder separates the space into inside and outside regions, and then in the outside region we have a certain behavior of difference, like for instance, say by C plus, C minus. Then we construct a very large oscillating forcing term in the inside of the cylinder, which creates a subsolution that goes with a very high speed, C plus. And then we can construct the example such that C plus is at least bigger than C minus, so that it creates a long fingering phenomenon. So we lose also convergence if C is thus positive in 3D or higher. And the natural question is, what if in 2D? So here we use the 3D, the high dimensionality of the problem. So what if the dimension is 2? Sorry, so before that, in the case of the non-homogenization in the limited setting, they're proven to be two different speeds, as upper bar and as lower bar, and there are traveling wave solutions following the speeds. This supported in disjoint sets. Here, the generalized means the waves are supported in only subsets of the ambient domain. And on the boundary, the two forces are balanced. And the head and tail speeds, which are identified as bars, exists in general media, and this is studied in Kao and Kim. And we consider the problem in 2D when the forcing term is just positive. And in this case, the homogenization is true. And the homogenization is proved by entirely different arguments. And this is also one of the main points of the paper by Caffarelli-Monneau, and there is another main point by Perturbation, which is that they noticed that the classical method does not imply the homogenization at least directly, and that there was a subtle issue of the symmetry operators. So they derived the homogenization by assuming a stronger condition, namely that there are perturbed characters. So also they assume the stronger condition, and for the positive forcing, they also prove the stronger condition. So they prove indeed there are perturbed characters for this problem, and then I'll discuss it in a minute. An operator is called a geometry if the operator satisfies this condition. So what this condition means that we have well-defined motion of the level sets, which means that even if we compose with some strictly increasing functions with the solution function, we still have the well-defined motion, well-defined level sets. So even if levels are different, the level sets are the same and their motion is well-defined. Another way of saying this condition is that it is degenerate in the normal directions. Here, the mean curvature operator is the most representative example. And here we have the trace of the Laplace of the Hessian X, the expression of X, and the diffusion. So it is diffusion, and the diffusion counts only the tangential interactions because we are excluding the normal direction. So it is basically the Laplacian in tangential directions or of the manifold. It is the mean curvature. And here the thing is, so we have a singularity at the vanishing gradient. So when p is 0, we have the singularity, we have discontinuity, and what Caffarelli-Monneau pointed out was this. So we have discontinuity at vanishing gradient. So they overcame this singularity by using this idea. Their idea was using inf convolution by balls or subconvolution by balls. So if L is a some value function, then L eta is defined as the infimum over the special variable running over the nearby points with radius eta. So that if the level set of L looks like this with the corners from above and below, then the level set of L eta becomes rounded from the below, so that it enjoys a regularization effect from the below. So L eta satisfies the one-sided Hessian estimates in tangential directions, and then we can plug in the Hessian estimates into these inequalities because the geometric operators can only tangential directions. So in the bottom of the line, we have the 1 over eta times the identity matrix, and so that we can plot the gradient on the very right-hand side. So during the proof, the gradient is pulled out on the right-hand side, and by dividing by the capital C lambda by some constant, the gradient is separated from the origin by some uniform constant. There was the idea of Caffarelli-Monneau, and Caffarelli-Monneau assumed one more condition, and here perturbed correctors are solutions to the corrector problem but now with the perturbed operators, and the Caffarelli-Monneau assumed one more condition of a uniform oscillation in perturbation parameter eta, and derived the homogenization under that condition. And here the oscillation is denoted by kappa zero, and it is assumed to be uniform in perturbation parameter eta. And under this condition, they prove the conditional homogenization. In the positive forcing case, as in Caffarelli-Monneau, the oscillation depends on the delta. Here, the delta is the infimum of the forcing term, and the delta can be thought of as kind of the coercivity parameter. And if we perturb the problem, then the forcing term is perturbed, so that it has the same infimum, it stays uniform. So delta is unchanged, and their oscillation is now uniform in eta, so that they could derive the uniform oscillation and that they could derive the homogenization for the positive forcing. However, kappa zero of the uniform oscillation parameter blows up as delta goes to zero. So if you lose coercivity, then homogenization becomes unclear. Here are recent studies of the Cavalier-Georgi equation. Recently, Itake-Muni transit U proved there's no well-defined effective burning velocity for the flame front for shell flows in 3D or higher, and the intensity of the flow is larger than a certain point. In 2D for cellular flows, Long-Senior proved that there is an effective burning velocity, and they obtained the uniform flatness behavior of the traveling waves. The effective speed is denoted by WH bar P, and E applies to every direction. So we know the uniform flatness behavior for every directions. And their approach was using game theoretic analysis, and they analyzed the game trajectories. And based on their method, they were able to control the oscillation of character. They obtained the uniform flatness in every directions. But for perturbed problems, it becomes unclear because game trajectory is also perturbed. So the proof strategies do not work and it's directly, so we don't know the uniform flatness behavior. So for this non-coercive equation, the homogenization becomes unclear. I'd like to introduce the use of approximate characters. I guess it appears many places, but here's one example in the literature. And this is about the quantification of the homogenization of first-order Hamilton-Jacobi equations. And the Capuzzo-Zeta-Ishii gave a rate of convergence for the first-order Hamilton-Jacobi equations, and they provided the framework on combining the doubling variable method and the perturbed test function method. And here, doubling variable method means that so we have a pair of variables x and t. This pair is doubled to have another variable, the pair of variables y and s, and we have that. And the perturbed test function means that we have the corrected part, like epsilon times of v of lambda. And they are combined, and we have the u epsilon minus u minus 1 times v. So basically, we are comparing the u epsilon and u plus epsilon times v. And it is compatible with the formal answers. And in particular, Capuzzo-Dolce and Ishii used the approximate characters for lambda for these reasons. Because the approximate characters provide for lambda, the solution to this problem, have these quantitative bounds. So as the direction changes, we know the rate of change, we know the quantitative change of the free lambda. And also we know the rate of convergence as lambda goes to zero. They studied the whole estimate based on the information of the approximate characters, and then they could close the estimate to derive a rate of convergence. So considering approximate characters has this advantage, and what if we consider just the characters? It's hard to expect these just the characters because there is actually the example of Hamiltonian where we don't have any regular selection of characters as the direction changes. There is no even continuous selection of the characters. And for us, the situation is similar because it is hard to expect the perturbed characters to exist for our geometric equations. But it is natural to consider perturbed approximate character because it at least exists and it is regular in the variation of p. And for instance, if lambda goes to zero, then it approximates a v of lambda. So the family of these perturbed approximate characters has these better qualitative properties. And now we want convergence, and this was stable for us. And somehow this idea makes sense because when proving homogenization, we already separate the local problem and the global problems when we already use the characters many times. And in particular, all the parameters like lambda and eta come from the local problem, and this is natural in the formal ansatz. And so we still have a chance to support the lower bound of the vanishing gradient separation. So it turns out it works. So we have this theorem. So if F satisfies these structural conditions, and if we know all the solvability of the character problems for every directions, then we can conclude the homogenization. So we can recover the classical belief even for the geometric equations, and in particular, as a corollary, we can conclude the homogenization for the curvature G equation with the 2D cellular flow, which was the main motivation of this study. And the next, for the first mean curvature flow with this country model, and if we assume this condition star, we know the equilibrium estimate of the characters and the approximate characters and the perturbed approximate characters, all the characters. We have the uniform Lipschitz estimate. So we have the quantitative bounds to start with, and we can start and we can derive a rate by adapting the framework of Kapsu-Dorset and Ishii, and yeah, we can derive the rate. And the next natural question is the optimal rate of convergence. And I think this is a hard problem, but one thing we can figure out from the radially symmetric case is that optimal rate is at least slower than O of epsilon because we have the log of epsilon term on the right hand side. Really, we know that if there is a null curvature effect, then the optimal rate is O of epsilon, and this is theorem by Tran Yu. In this case, the first order convex Hamilton-Jacob equations, then the problem is about a metric from a point to point. And the theorem by Tran Yu provides the additivity of the metric through curve cutting lemma. They decompose and they rearrange the geodesics to prove the super additivity, which is non-trivial from the metric structure. And this is a fundamental understanding of the metric, I believe. And also, I think that the optimal rate with the curvature effect also asks a fundamental understanding on the competition between the curvature effects and the forcing term in large scale. And the slowing effect of the right-hand side at least tells us that the curvature effect is still there and affects the problem in large scale. So the problem is not exactly like when there is no curvature effect. So there are different problems. Let us outline the proof of theorem one, which is about homogenization assuming only characters. We want to prove that this less limit u upper bar is a subsolution. Then we have the u upper bar is less or equal to u lower bar by the comparison principle. U upper bar is subsolution, u lower bar is a subsolution. So that their agreement it gives a certain function, which is the limit function. So we have the convergence. So we assume for the contradiction that the u upper bar fails to satisfy subsolution test somewhere, say at a spatial point at some point p0. And now we want a contradiction. And also we consider the case when the effective value F bar of the direction is strictly positive. And we can prove the other cases similarly. We can change the direction of any convolutions by poles. And also we consider the perturbed approximate characters, which is defined to be the solutions to this problem. And we take eta small enough that we have this property. And here theta is from the hypothesis for the contradiction. And here we have theta. And we are using it critically. And also we're using the positivity of the effective value, and we have one more positive uh, constant, which is kappa zero, which is from the uniform oscillation of the character. So we are also critically using there is a character. Following the doubling variable framework, we consider this function. And here L is a planar traveling wave, and we have effective speed that is approximated by negative lambda times we have lambda and eta. It approximates the effective speed at bar p. And L tilde is with a character term, and so it is so almost planar profile, and then we have approximation of effective values and the characters, and they are not exactly the same. So there are some small errors, and the small errors are encoded in the function psi in the last term of the definition of U bar. After considering all the errors, and then after that we take the subconvolution by Bose sorts to obtain U hats. Then by the Hessian estimates, these sets, so the derivatives of U hat satisfies the Hessian estimates. And the function has a maximizer and it satisfies this order of limits. So if we take the limit as sigma goes to zero first, and we have this, and then we take the sigma goes to zero next, and we have this limit, which is p0. And by the standard framework of physical solutions, we apply the Crandall-Ischi's lemma to find the proper z's to work with, and we put the derivatives into the subsolution test and into the super solution test. So we have two inequalities of different size, and we subtract them, had to have this one-sided inequality. So in particular, we have the difference of the f stars in the middle of the left-hand side. And f bar is supposed to be some lambda times of v of lambda times lambda of eta, but it approximates the effective value with some small errors, and the error is 1/8 theta, which is small enough. And it is moved on to the right-hand side. So we have that, and here the first and last terms are phi time derivative phi plus f bar p, which is theta. So if we can kill the difference in the middle, if it is close to be zero, then we have the theta is bigger than 1/8 theta, which is a contradiction. So once we kill the difference, then we are done, and we have the information of the derivatives. This is from the Crandall-Ischi's lemma. Here is the re-display of the difference with the information of the jets. And if we consider some complete models, for instance, with the curvature operator, then the difference looks like this. The difference is the trace of the difference of the gradient hats, which is the p over the modulus of p times the Hessian. And the concern is if we take the sigma to zero first, as in the first limit, and we lose the boundiness of the estimate of the Hessian, so we don't know the boundiness of the Hessians if sometimes y in the second term in the trace. And another concern is if we take the limit sigma to zero and it's done to zero, then P2 approximates P1. That is good, but P1 hat, we don't know if P2 hat it approximates the P1 hat because P hat, the function P hat is discontinuous at P0. So there are two main concerns, and both of the terms are not nice. So, but if we introduce this relation with another parameter by perturbation, and the Hessian bounds becomes uniform Hessian estimates so that we can take the limit as sigma goes to zero. And also we can separate the gradients from the origin because the x is found from the sets of the subconvoluted function. So we can plot the gradient on the right-hand side. And on the left-hand side, this is from the supersolution test of the corrector, and the effective value is positive. So we can connect these inequalities, and then we can separate the gradient. So P2 is uniformly far away from the origin. So P2 approximates P1, and P2 hat approximates P1 hat. So in the middle, the difference of the P hats are cancelled, and we have the boundedness of Hessians. So the trace becomes zero in the limit. So we can derive a contraction. Now we discuss the rate of convergence of first Minkowski flow. We follow the framework of Cappuccino-Tanishi, and the basic starting point is that all the perturbed equations are still coercive, so that they have perturbed approximate characters that are uniformly reaches continuous, also in eta, and approximate characters enjoy these bounds as well, so we can start. Maybe the most complicated part is the gradient separation from the origin because we have give the quantify the version of the gradient separation. To achieve this, we take this convolution of U epsilon and we consider L as before, and we have the constants, but they are associated with the epsilon with some powers, with some multiplicative constants. And here on the very left-hand side, the gradient is separated. The gradient is pulled out because x is the jet of the subcompleted function. And then we can link all the inequalities to the right-hand side, which is supported by some constants times epsilon times some power. So we can track the separation of gradient in the power of epsilon. And we can continue the track, and then we can close the estimate. So then we can derive the rate. And let's look at the example. This example is the radial symmetry. So we have an arrangement of both the various radii. So the equation becomes the first order Hamilton-Jacobi equations because the curvature terms becomes 1 over r. And also the Hamiltonian is concave. So we have this optimal control formulation. And if the curve does not satisfy this velocity condition, then the Lagrangian is a negative infinity, which you can ignore in this prima. And actually, the curve must go up as fast as possible to achieve the prima. So we can think this curve denoted by psi1, which solves this differential equation, and this psi1 is the optimal curve. So we have this representation for the value function. And here in the equation of psi1, we have a -1 and the plus 1 over psi1, and the -1 is from the forcing term. And the 1 over psi1 is from the curvature effect, 1 over r. And the thing is that they are in the opposite directions so that they compete in large scale. And actually, the logo epsilon terms come from the accumulation of these curvatures, and the integration of 1 over r is log of r, so we have log of epsilon in the opposite direction of the forcing term, so they compete. So the curvature effect drags the forcing term effect. So it slows down and the affects in large scale. And so we can see the effect of the curvature effect in the large scale, and yes, and I think the obtaining optimal rate is another problem. So this is the end of presentation. Thank you.
Okay, thank you, Jiwoong. We have plenty of time for questions. Are there questions or comments for Jiwoong? Can you unmute and ask him? Okay, why we are waiting, because you mentioned your main motivation was from the curvature G equation from the work of Gao Long Xin Yu, right? And then the other work by um, Mitake Muni, Tran Xin Yu. Can you explain the model? Because you went a little bit quick over there. Just explain the model for the cutoff G equation, and then why is it sort of, I mean, why you know um
So for the curvature G equation, we have the wind is from the problem. So for instance, in 2D, so we have the cell, and the wind is also the same periodic. So wind is circular, and like in this direction, and we have a lot of cells. We have a certain arrangement, initial arrangement of the hyperplane, and it goes through the traveling by following the equation. There are many copies of the cell, and the hyperplane to front will go through the effect by the wind. It's unclear to have if we have a uniform fluidness behavior. What they proved that if they have certain solution to the local problem, say V, and for this one they proved that the magnitude of the character is uniformly bounded. For this purpose, they use game theoretic analysis.
Yeah. Okay. Thank you. Are there other questions for Jiwoong? Or are there other comments?
Okay, so maybe I ask questions. So those for the periodic case, like can you method to do for like a random case?
For the random formulation, so we would need to think about the limit problem, which is the cell problem. So we need to think about the correctors. I believe that's a pretty good question. The only state's answer is I don't know, and I believe that's a great question. But we need to control the oscillation of the increasing term, and we need to somehow to obtain that the character is enough for the homogenization, and we need to see the gradient separation argument in the probabilistic formulation. At least it is probably avoid the vanishing gradient in the probabilistic formulation. I guess that should happen first, and yeah. Besides that, I honestly don't know.
But the conclusion is similar, right? So say the random case, there's cell solution to the cell problem, and then the homogenization holds, right?
I guess so. As long as we have a real behavior of the approximate characters, even in probabilistic formulation, then we can we can expect to apply the same arguments while considering the perturbed approximate characters. But
Okay,
in the probabilistic formulation, we have to think about the local problem and its behavior.
okay, I see. Thank you.
Yeah, maybe just the final follow-up question, because as you said, right, from the result from Gao Long Xin and the other result by MMTXY, essentially, can you go to your theorem one that is sort of your theorem is an improvement of the seminal result by Caffarelli and Monod, is that if your corrector has a solution, then you have homogenization, right? So a follow-up question like what Yifeng asked is that if let's say you have the approximated corrector lambda v lambda, that you have solution to that, and lambda v lambda is conversion to minus f, then perhaps you also have homogenization, right? Because that's gonna work for the random case.
That's gonna work for the random. Yes.
Yeah. So in other words, you can more generalize your theorem one to a weaker statement too, with only lambda v lambda.
Yes.
Okay. Yeah. Okay. Good. Yeah. Okay. I got it. Thank you.
Thank you.
Okay. Yeah, if there's no other questions, then I think it's also a great time to end. So thank you, Jiwoong, and thank you everyone for attending. It's the end of the semester. I know everyone is busy with finals and gradings and whatnot. So still, thanks a lot for attending. Let me stop recording.